Okay, so it appears that this video covering this little lecture here didn't actually work out for some weird reason. I don't know why this happened, but there was only video for the first couple seconds, and then the video cut out. So I'm going to record this. I'm going to record another video, but I'm not going to redo these notes. So I'm just going to go through it and discuss what we talked about on the other video. So I began by stating, so here we are, we're doing hypothesis testing, and I'm gonna begin by stating we have three types of problems. We have a right tail, a left tail, and a two-tailed problem. So beginning here with the right tail problem, this is the problem that that's similar, well, that is the same as the example I did above here for the pipe problem, where the critical area is to the right. That's called a right tail problem. So when your critical area is to the right, so it's the right tail of the distribution, then you're going to have a null hypothesis and an alternate hypothesis. And your null hypothesis, and in every one of these types of problems, the null hypothesis is always the mean equals some constant value k. What changes is the alternate hypothesis. So our alternate hypothesis here is the mean is greater than k then. So the condition where we reject the alternate hypothesis, so for a right-tailed test, the condition where you reject the alternate hypothesis let me write out this a little further. Reject the null hypothesis when your test z. I'll actually write this out. Your test z is greater than z crit. That'll put your test z in this critical region somewhere over here to the right of z crit. So if your calculated test z ends up to the right of z crit, you reject your null hypothesis. And then what I've done is I have shown you what the for given alpha value, what the critical z value is, because the critical z value is always going to be the same for a given alpha value. And remember, alpha is equal to so if alpha is equal to 0.1, for example, or 10%, that means this is 10% of the area of the curve over here. So it's 10%. Z critical, the z value, the left boundary of this region, is 1.28. That's always going to be the same. And remember, we discussed alpha before. Alpha is the alpha always what's nice about this testing in this way, where we set up a null hypothesis and an alternate hypothesis, alpha equals the chance for making a type 1 error. Okay, so I guess I should mention these other two too. So if alpha equals 0.05, then the left boundary is 1.65 here. And if alpha equals 0.01, then the z critical value is 2.33. So notice there's only one tail, so alpha is taken up only on one side of this distribution. Okay, the second type of test we call a left tail test. See if I can scroll down to it. Left tail test here. So this is the opposite situation of the above. In this case, your null hypothesis is still the same. You're still going to have the mean value equals some constant value. But now your alternate hypothesis you're looking for is a mean less than this value of k. So the critical region then that we look at is over here on the left, and it could be the same alpha value depending on the level of significance and how accurate you want to be in your analysis. But in this case, then you reject your null hypothesis when your test z is less than your Z critical here, because that'll put the test Z then in this critical region. So that's when you reject your null hypothesis there. And alpha for point 1 is going to be the same as it is up here. The Z critical is going to be the same as it is up here, except it's going to be a negative value. So this Z is going to be negative because it's to the left of 0 here. Remember, in the standard normal distribution, your mean is 0. So values to the left. So this is like a standard, one standard deviation and 0.28 to the left of 0. When alpha is 0.05 or 5%, we got minus 1.65, which is symmetric to this value. And then when alpha is 0.01, we get minus 2.33, symmetric to that value. So it's the same methodology otherwise. The only difference is that your null hypothesis is stated differently, and the idea you're looking for is to determine if the mean is actually less than some originally stated population mean. Okay. And then here is the third type of problem. In this problem, we have a two-tailed situation, and we actually split alpha up. So we divide it by 2, much the same as we did with a confidence interval approach. So alpha is divided by 2. So now these regions here, when you're dealing with a level of significance of 0.1, for example, the alpha in these regions are going to be 0.05. So when you're dealing with an alpha of 0.01, then your Z critical is going to be slightly different. And for example, at alpha of 0.1, your Z critical will be shifted 1 to 1.65, because the area, if you look up here, when this area is 0.05, that's what this area will be when alpha is 0.01. This area will be 0.05. So your Z critical will match the situation of 0.05 up here of 1.65. And it does, except that now it's a positive and a negative 1.65, which means Z on this side of 0 is going to be positive 1.65, and Z on this side of 0 is going to be negative 1.65. Well, continuing down, 0.05, we get plus or minus 1.96 for your critical Z, and 0.01 is plus or minus 2.58 for your critical Z. Now, I guess I hadn't mentioned this yet, but the null hypothesis, again, is the same, where the population mean is equal to some constant value that you're at, and you want to determine your alternate hypothesis is that it does not equal that. So you potentially, your test Z could be over on this side of the plot, or it could be over on this side of the plot. It just depends how it turns out. And in either of those situations, if your test Z was greater than, so we're going to reject the null hypothesis when Z test is greater than, I guess I'll call it Z crit, the positive 1. So like when it's greater than positive 1.64, or when your Z test is less than your Z crit negative. So if it's less than the negative, so if your Z crit falls into any of these two critical regions, that's when you reject your null hypothesis. Okay, so that's essentially what was in that video that didn't work well. I'll go ahead and post this and replace it.